much. My name is Wei Fu. Great to be here. My topic is ground state electro-optical conversion, and I work in Professor Hong Tang's lab at Yale University. And this work is in collaboration with Professor Jiang Liang's group. So the motivation of our project is to transmit quantum information from microwave domain to optical domain. And an ideal quantum transduction has two requirements. The first one is we want the conversion efficiency to be high. And the second one, we want the converter to be operating in its quantum ground state. So for the first one, intense optical parametric drive is routinely required to enhance the conversion, as shown in our previous work. As we can see, when we increase the pump power, the conversion efficiency also goes up. But unfortunately, this work is done at 1.7 Kelvin, so it's not at its quantum ground state. In order to realize quantum ground state, we have to install the device in millikelvin temperature. And this is extremely hard because the thermal conductivity of the device is proportional to temperatures cubed. And the cooling power at such low temperature is limited to around 10 microwatts. So this cooling power is sometimes even lower than the power of the optical parametric drive. So the challenge here is how to boost the conversion efficiency while maintaining the converter at its quantum ground state. So to address this problem, we first wanted our device to perform well. To do this, we choose the aluminum nitride and niobium nitride material platform, which can provide a very high electro-optical coefficient and also high quality factors for both optical and the microwave mode. Also, our design can be integrated in a chip so that the mode volume is small and the interaction between microwave and optical mode are maximized. Second of all, instead of use a continuous optical drive, we use a pulsed drive, and by choose the duty cycle of the pulse to be low, we essentially reduce the optical power that's being sent to the device. So here we do a comparison between the continuous drive and the pulse drive. We can see that by using the pulse drive, we can send a much stronger pump to the device, and the conversion efficiency is improved by more than 1 order of magnitude. And the highest conversion efficiency we demonstrate in this work is 0.15%. Also, the pulsed drive can help us maintain the device at its quantum ground state. Here's another comparison between the continuous and the pulse scheme. And we can see the power handling capability of the device is improved by more than 30 dB when we use the pulse scheme. And even at optical peak power that's comparable to the cooling power of the dilution fridge, which is around minus 11 dBm, we can still maintain the microwave cavity of the converter very close to its quantum ground state, with the thermal occupancy less than 0.1. So the next task we want to address is where does the residual noise comes from? And to do this, we did a time evolution study of the output spectrum. And in this study, we found there are two different thermal bands in the system. The first one is the faster response effective band, which is established immediately after we shine light on the device. And another one is a slow response effective band, which can be attributed to the heating of the whole converter device. And by comparing the magnitude of these two effective bands, we can conclude that the majority of the noise comes from the faster responsive band, which is caused by the superconducting absorption of optical photons. So this study, this conclusion help us provide us some guidelines of how to design our future device. For example, we need to better shield our microwave resonator from the optical light source in order to get a better power handling capability. So to conclude, in this work, we use a pulsed drive and improve the efficiency by 1 order of magnitude and the power handling capability by 3 orders of magnitude. And we realize efficient microwave to optical conversion with converter in quantum ground state. And we found the major source of the thermal noise. Also, the study provides some guidelines for future microwave to optical converter design.